Alright, section 10.2 on regression. I decided to make this video because sometimes the textbook videos are getting a little bit off target of my instructional strategies, which I'm more of use technology to solve the problem kind of piece. So instead of piecing together notes from their videos, I decided just to kind of take and put the notes together. So you can use your study sheet and fill in. I left some blanks off on your study sheet or your homework guide, so that way it forces you to pay attention, I guess. Here we go. Two things that you should be done before one performs a regression analysis. The first thing is you need to construct a scatter plot, and that's our number one thing. They're going to have you practice doing scatter plots. It's not a necessity every single time, but what the scatter plot does for us is we get an idea if you have some kind of relationship. And so the relationships that you might see are a positive linear, a negative linear, a curve linear. So in this case, there is just basically where you get a scatter plot and you see the curve. We've already talked about negative and positive relationships, and you'll see that in just a few moments. And then, of course, a zero or a no discernible relationship, where you got things kind of all over the place, scattered. So that's the main thing you want to look for, because if you do the scatter plot and you don't see any relationship, then there's no need to continue forward with the calculations. So our second thing would be then, if we feel like we have a relationship from the scatter plot, then we can go ahead and test the significance of the correlation coefficient. And so in this case here, a couple reminders is, if the value of the correlation coefficient is significant, then the next step is to determine the equation. Well, what does it mean to be significant? Well, when we find that correlation coefficient, we are looking to see, are we at 0? Are we over at our far left at the negative one? Are we over at the far right at the positive one? Keeping in mind that as your correlation coefficient increases from 0 to 1, so as you go from 0 to 1, the points on the scatter plot are going to get closer and closer to each other. So this is a great analogy. So here we see that this guy has a correlation coefficient of 0.5. This guy has a correlation coefficient of 0.9. And this guy has a correlation coefficient of exactly 1. And same for a negative. So as you go from 0 to negative 1, we're going to see the same situation, and we can see that from our little image here, is that this is negative 0.5, this is negative 0.9, and this is negative 1. So this is a strong negative relationship. And then, of course, as the closer we are to positive 1 or the negative 1, the more accurate our prediction value will be. So the whole idea here of what we're looking for in this section is we've collected this sample data. We want to make an equation from this sample data, and from that equation we want to be able to make predictions. And so we're going to see that here as we keep going on. That prediction leads us to this thing called a line of best fit. And so a line of best fit is essentially, if you imagine you've got this scatter plot and you're trying to determine like how you could draw the line. So like, would my line of best fit be, would it be line number 1, would it be line number 2, or would it be line number 3? And obviously if you look at line number 2, you can see that it fits this idea of the sum of the squares, or the vertical distance each point lies from this line of best fit. And so you can see it's kind of like finding the best line, so that when you add up these differences, you figure out that it kind of all balances out to be the best situation. From there, what do we do? How do we calculate that regression line? Well, we've seen this calculation before when we were doing our correlation coefficient. Now, once again, we will use our calculator for this, or easycalculation.com, and so I'll have a separate little video to kind of demonstrate that. But just for the conversation purposes, here is our regression line equation. Our a value, it's read as y prime, where a is my y prime intercept. So that means like where I cross the y-axis. My b is the slope of the line. So that's how steep my line is. Like, is my line like this, or is my line like that? And then last, the sign of the correlation coefficient and the sign of the slope of the regression line will be exactly the same. So if I have a regression, a correlation coefficient that's positive, and I'm just going to say 0.5, then my slope, in this case, like I have here, would be positive. And there's no correlation there, there's no relationship. I just arbitrarily made up that 0.5 for discussion purposes. Same here, if my slope or my correlation was negative, so we'll say negative 0.5, then my slope, my b value, would be equal to negative 3.622. The key thing is negative. They're both negative. Let me make one quick correction. That's the algebra in me. That is my b value of my equation. Excuse me for writing m. Okay? So, a couple things, little factoids to think about there. Alright, so we move on to these assumptions and the assumptions that we have, and this is really just vocabulary. This is understanding what you're doing in the study. There's no necessarily application here that you need to worry about. This is kind of like the foundations of where it builds from. So our assumptions, if we're gonna make predictions, our information has to come from a random sample. We know that, we've already talked about that. For any specific value of the independent variable x, the value of the dependent variable y must be normally distributed about the regression line. So normally distributed. So I had a note here thinking about point or figure 3. Let's see. So normally distributed, they just kind of think about this little curve. Don't, like I said, don't get real in the depth and it'll knock you down. This is more of a vocabulary question. Okay. Last one. The standard deviation of each of the dependent variables must be the same for each value of the independent variables. And so standard deviation is the average distance that you are from the mean, essentially. So once again, don't sweat this. This is just a sketch. Once again, it's the facts. Fact 1, fact 2, fact 3. Use these facts to make sure. Don't stress about how these things down here are calculated. So our regression line, this is a factoid once again, this is not an application piece. The magnitude of the change in one variable when the other variable changes exactly 1 unit is called marginal change. So our key thing there is marginal change. The value of the slope, b, of the regression line equation represents the marginal change. So our slope here determines how much we are increasing. So how much we're going to go up on the y and over on the x. For valid predictions, the value of the correlation coefficient must be significant. So keep that in mind. If we go back a couple slides and we think about this, in order for our predictions to be valid, we've got to be out here in this critical region when we think about that distribution. When we're solving the problems from 10.1. If we're not out here in the critical region, then we really probably have to reject, we'd have to accept our null hypothesis, and so we really can't roll with this and say, yeah, this is going to work, these are great numbers, this is going to fit the population. And last one is, when r is not significantly different from 0, the best indicator of y is the mean of the data values of y. Okay? Factoid. Don't get caught up in the facts or in the pictures or the concepts. Just go with the fact. Alright, so last little piece here, extrapolations or future predictions. This is a factoid again, so nothing big here, just making sure we have these concepts in our head, alright? So, sorry about that. Extrapolation, or making predictions beyond the bounds of the data, must be interpreted cautiously. So, slow down and read that again. Making predictions beyond the bounds of the data. So, here's a funny little clip that I came across that in your textbook is, explain that to me. So, we've collected data, we've charted it, and then you see this crazy thing happen, which is completely different than the data that had come previously. So it's kind of like making a future prediction. Well, what caused this to happen? There's many things that could have caused it to happen. So we have to be very careful about interpreting things from our data unless we feel like we've got some really strong indicators. Remember that when predictions are made, they are based on present conditions or on the premise that the present trends will continue. The present trends will continue. This assumption may or may not prove true in the future. So here's another example. It is estimated that wearing a motorcycle helmet reduces the risk of a fatal accident by 30%. So does that mean that that fact is going to hold for in 2016? What if that fact was from 2013, and since then there's been changes in motorcycle suspension or visibility or whatever, and so now that percentage has changed. So we have to be careful about looking at data and making assumptions based upon something that may change, that may not be consistent, and so we have to be careful about that is what we're saying.